fellow hominids. Tonight is a short discourse on some core pieces of philosophy of science. The question is, what is philosophy of science? But before we can get to that interesting tidbit, we must first ask, what is philosophy? Philosophy, as its Greek roots imply, is the love of wisdom, the love of concepts of finding truth. Now, philosophy can be summed up in a fancy way by something called reflective equilibrium. It's a fancy word for basically introspecting on your own ideas, for looking for new evidence and facts and systems, and then updating your beliefs based on those new facts and evidence. An example might be if you believed that the Earth was flat, and if you were a philosopher and you believed that the Earth was flat, and you were okay with the idea of reflective equilibrium or introspection, what you would do is you would examine your beliefs, and you would examine the world around you, and listen to other ideas, and upon finding out that shadows aren't the same length at the same time of day at different points on the Earth, you would be an anomaly either in the sky, either there's a giant glass prism distorting light, either light curves, or the surface of the Earth itself is curved, and then you would update your beliefs. And you would continually do this as you updating your beliefs, and you would get closer and closer to the truth. Hopefully, you would have the best possible beliefs. That's all reflective equilibrium and philosophy is in a nutshell. The next question we must ask before we can get to philosophy of science is, what is science? Science, basically, is the best known and most effective predictive model generating tool of the natural world. It is a cumulative process that takes place over several years, whereby individuals formulate hypotheses and theories and test them, and work forward toward moving towards the common goal of understanding reality and understanding nature better and making better predictive models. Science is not a truth generator. For people who only have a casual interest in science, and certainly for me when I first learned about it, the fact that science is not a truth generator was kind of shocking. I mean, truth in the sense of logical imperatives that cannot be denied. Truth in the sense of all bachelors are male and single. That's a logical truth. You can't get around that. Science does not and cannot generate those kinds of truths. What science can do is give you a model that can give you predictions based to allow you to try to predict what reality will do to a certain degree of resolution. Science is also not ideas, because you see, it's also not the context of discovery. Ideas can be thought of by anyone and can come from any context. Idea generation is not a rational process. You can come up with ideas while walking, while taking a shower, or having a conversation with friends. A hypothesis alone is not science. Science is the process of creating a testable and working theory. Now, the next question is, how does science work? Science works mostly by induction. An example of induction is if you were a scientist and you want to understand swans and swan coloration, you would be looking at swans and you would notice that every single swan you've encountered is white. And you would say, well, maybe all swans are white. What you've done is created an inductive statement. However, the problem with induction is that it's weak, because the moment you encounter a black swan, your theory that all swans are white based on all known evidence becomes false because you got a new piece of evidence. Induction only works as well as the amount of data points that you have. But this also is the strength of science. So back to philosophy of science. Philosophy of science is where we take philosophy, with what I mentioned earlier, that introspective, that reflective equilibrium, that ridiculous term, and we apply that to science. We look at science itself, the processes, the experimentation, the theories behind it, the induction, and we ask, why do we do this? How does science work? What could we do to make science work better? Is this the best thing we can do? What is science? Those kinds of questions that philosophy asks, and we take them and we apply them to science, and then you have philosophy of science. So it also asks questions like, how can we justify our scientific ideas? Are beliefs grounded in anything more than what we just our mere imagination and what we want? One of the fundamental goals in philosophy of science is the demarcation problem. That is, how do we demarcate or draw the line between what is science and what is non-science? And a classic example is astronomy versus astrology. And demarcation is all about this. In the early 20th century, in the early 1900s, Karl Popper kind of led a sort of revolution in understanding the new demarcation problem. He considered the demarcation problem to be the fundamental, or one of the fundamental problems that needed to be solved in philosophy of science. So he proposed this idea that for something to be science, for an idea to be science, it has to be falsifiable. And we call this falsification. And the idea is that if a hypothesis or a theory cannot conceivably be falsified in some way, then there is no way to then it's useless, it's meaningless. An example might be with, say we had a hypothesis, all swans are white. Now this is a scientific statement because it is falsifiable. We can go out and look for swans that are not white. There's a way to falsify the statement. So it's a scientific hypothesis. Now, it's not valid in the sense that it's not true. So you can throw it away as a functioning hypothesis. But because it is falsifiable, falls under the logical domain known as falsifiable hypothesis, and we can use that as a useful, it's a scientific avenue you can pursue. How can this be made false? Every single working scientific theory can be falsified. General relativity, Newtonian mechanics, they all have properties and rules and expectations. And the moment you find something in nature that can make that false, then you have new data with which to move forward. Now, the pros of falsification are things like rapid iteration, and it's also very extreme sense. It's an extreme instance of the spirit of reflective equilibrium. You rapidly update. Every time you find something new, you change your beliefs. But there is a con to extreme forms of falsification, and that is it's easy to rescue your theory by just changing it in the face of evidence instead of doing some hard work and trying to understand what the case actually was. A good example of this would be when before general relativity came along, Newtonian mechanics was used to predict the orbits of planetary bodies. And we could see the planet Uranus with a telescope, and we would watch its orbit, and we noticed that its orbit didn't follow the path predicted by Newtonian mechanics. So scientists said, well, since we don't have another theory of physics, then there must be some body out there, some gravitational body that we don't know of yet, that is disturbing the orbit of Uranus. And a few years later, they managed to discover Neptune. But the same thing happened again with the planet Mercury, the one closest to the sun. and scientists too noticed that its orbit was, Mercury's orbit was irregularly shaped. It wasn't going as exactly predicted by Newtonian mechanics. So, as they had done previously, scientists predicted that there must be a gravitational body disturbing the orbit of Mercury, and they called this yet discovered body, they called it planet Vulcan. Well, with the rise of general relativity, it turned out that there was no planet Vulcan. There's nothing there. And Newtonian mechanics is insufficient to predict and simulate the orbit of Mercury. However, relativity, the new physics theory proposed by Einstein and others, was able to accurately predict Mercury's orbit and explain the strange disturbances that Newtonian mechanics cannot account for. That's an example where, in that case, the Newtonian mechanics was falsified and had to be thrown out. And that's where you have to be cautionary. Just because you find some data that falsifies a theory or hypothesis, you don't immediately throw it out. You see if you can work it out. Is there an unknown planetary body? And if you experimentally can't discover that unknown planetary body, then maybe you have to modify the theory after that. But you have to be, you can't be too hasty, which is what I mentioned earlier about one of the cons of over enthusiastic falsifiability. Before I continue, I want to get to this one, but before I continue, there's a couple of new schools of thought regarding the nature of science and defining whether or not a particular hypothesis counts as a scientific question, and that is there's post-positivism, which is spearheaded by Kuhn and a couple of others. I don't remember the names, and Bayesian probability. Post-positivism is a response to falsifications, over-eagerness to throw out theories, and a response to early logical positivism that was incompatible with the fuzzy nature of experimental data. And basically tries to take into account certain aspects of social constructs and certain aspects of the way humans are involved in science, and take that into the understanding of defining what a scientific question is. Because, to quote Kuhn, it is in normal science that Karl Popper's sort of testing does not occur, and that is the utility of scientific paradigm is the utility of a scientific paradigm is for the sake of puzzle solving, and it suggests solutions to new problems while continuing to satisfy all the problems previously solved by the paradigm replaced. So basically, post-positivism takes falsifiability as a toolkit and tries to gently move forward and cautiously move forward rather than be over aggressive about throwing things up, if I've understood it correctly. By the way, just as a disclaimer, you shouldn't believe anything I say. You should absolutely do research and look it up, because between my own personal misunderstandings and slips of the tongue, you can get the best picture and the clearest picture by actually reading source material. And it's a lot of fun. All right, now this slide and the next slide are what I wanted to get to. There are two big camps in philosophy of science, the realist and the anti-realist. The realists believe that science is a useful approximation of reality. They believe that science and the results that we get actually approximate reality, like our models. To give an example, concrete example of realism, that would be Newtonian mechanics gives you accurate predictions to a certain resolution, to a certain decimal level, or certain deviations per per amount of precision. Precision being smaller and smaller measurements. And Newtonian mechanics is only accurate up to a certain level of precision. After that, reality deviates from the Newtonian model. And so you could say that, Newtonian mechanics, a realist would say that Newtonian mechanics is approximate to reality up to a certain point. And the point of science is to create models that are more and more and more precise, that better and better and better approximate reality. The anti-realists are, despite the name, are not they're not people who think that reality is not real. They're not simulationists. Anti-realists are they are against the realist position. The realist position that science is a useful approximation of reality. The anti-realist position is that science is merely, which means only, is merely a pragmatic enterprise that happens to generate useful, functioning theories. Newtonian mechanics works from a human perspective, whatever human perspective is. However, because reality itself, as the anti-realist would say, is ultimately unknowable, no theory that any human can make can be a useful approximation of reality. It just happens to work. The realist argues against that and says it would be an extraordinary, ridiculous miracle if science wasn't a useful approximation of reality. It would be an extraordinary miracle if that was the case, because we are constantly producing better and better models that better and better predict reality. The anti-realist then uses what's called pessimistic meta-induction. I actually glossed over that term, and it wasn't until I read and heard about the rest of the anti-realist argument that I began to understand what pessimistic meta-induction meant. Now, pessimism is negative, it's bad, it's trying to take the worst possible view. Meta is applying the following to itself. So we know what induction is. It's taking a small body of knowledge and then extrapolating a large amount. You see 100 swans, they're all white. Okay, maybe all swans in the entire universe are white. That's induction. Now, pessimistic meta-induction is where you do induction about induction. So what you do is you look at the history of induction, and you notice that induction is wrong all the time. It produces very unreliable results. Swans are not actually all white. And therefore you go, well, fine. I'm going to take the worst possible view and say that induction is impossible, induction is ridiculous, and since science is based on reduction, science cannot actually approximate reality in any meaningful sense, and it just happens to generate useful models as an accidental byproduct. And that's the anti-realist position. And I forgot to switch to the cool slide. Oh well. Basically, yes, the anti-realist position is that science just happens to generate pragmatic models, and the realist position is that science is an ever-increasing accurate approximation to reality. Now, I want to inject some of my opinion here, sworn in there, and the anti-realist versus realist argument seems to me to not address the issue in a way that I would like. I'm not sure what the exact problem is, but okay, let's suppose that we exist. We're not all solipsists, okay? Or I'm not the solipsist here, or whatever. We exist in some sense. Let's assume that. And we call the nature of the universe, whatever it is, we'll call it reality. Just apply a label to it. And so reality exists. And let's assume that reality has some measure of consistency as well. So, the Earth will continue spinning with certain properties. There's momentum, certain things that have a sense of consistency. Now, if that box is reality, and we build models in our minds to simulate and to predict parts of that reality, it seems that whatever the actual fundamental nature of reality is, whether it's a simulation in the mind of a computer, in the mind of God, or in the ether, or if it's quantum fluctuations, or if it's something even deeper than that, whatever the ultimate nature of reality is, seems to me that from the human perspective, we are able to create models that predict things that we can detect in our experience. So whatever science does, whatever the models that we are creating do, it seems to me that they are approximating something, and that something is part of reality. Maybe it's not the fundamental nature of reality, but it's certainly part of reality. So to me, the anti-realist position, which seems to be to throw your hands in the air and say, well, it's nice, it's practical, but it doesn't really approximate reality. We can't ever know. Induction's impossible. Seems kind of a defeatist attitude, and seems to ignore the fact that science is predicting something that we are experiencing. Maybe it's not the deepest level of reality. Maybe we'll never know that. But it is, I think it is approximating something, and that's opinion. All right. As I mentioned, there are some other, what do you want to call them? There are other models of science, Bayesian probability, and I can't remember the name of the other one, but Bayesian probability, basically it's an equation that was created by a minister in the 18th century, and it takes in numbers called priors, which are based on experiments and evidence, things that you know about reality, that you have some measure of confidence in, and then you weight those priors with your confidence levels in them, and you get out a number, a probability distribution that you can graph, and it's kind of nebulous or whatever. It would look like a kind of like a cloud, depending on the amount of weight you put in each probability, and it would allow you to say, rather than say this is true or this is false, you say I have a confidence level of 90% or 50%, and then rather than going about like a logical positivist and making logical claims about reality, which is hard to do, you instead say I have a certain level of confidence in something. And you make predictions based on that, and you make decisions based on that. When someone says, to give an example with atheism, someone asks someone who's used to Bayesian reasoning, do you believe that there is no God? Can you confidently state that? And they'll say, no, based on the priors that I'm aware of, history, science, evolution, historicity of religions, other religions, my priors give me this much confidence based on the amount of evidence that there is probably not a personal deity, and then that would be the Bayesian position rather than yes or no. It tries to recognize that knowledge, human knowledge and understanding, is based on limits and probabilities. Anyways, thank you very much for being patient and for listening. We will now open it up to questions and discussion. But first, do you think there's anything I missed, Caleb?
No, I know you covered the basics really well. One thing that I would add is that the camps maybe aren't quite as distinct as their names would imply, and that a lot of people operate within multiple camps at the same time. So for example, when I do research, all of our statistics are based on Bayesian problems. So I'm 95% confident that there was a difference between group A and group B, for example, if I'm testing how to do treatment or something like that. But we're at the same time, we're making very falsifiable claims in order to try and test them and say, okay, we're trying to falsify this, and we're this confident that we did falsify this. Does that make sense? So the sort of the philosophy aspect of it is fairly distinct, but the actual on the ground nature of what's happening is a little less distinct.
Okay, so to rephrase what Caleb said, what he does in his lab, he uses Bayesian probability to